Hello everyone, welcome back to Nuclear Reactor Kinetics and Dynamics lectures. In the last lecture, we began generating Bode plots to plot the gain and phase of different S-domain polynomials, and today we'll continue this adventure into the land of Bode plots. In this analysis, our control elements generally contain the following classes of frequency domain polynomials. We discussed how to generate Bode plots for the 1 over s function in our last lecture, and today we'll see how to generate Bode plots for these other polynomials. As we'll see, it's generally helpful to rewrite these functions in the following form so that we have 1 plus s divided by omega naught terms in the denominator, where omega naught equals the natural frequency or breakaway point of the plot. The squiggle term here represents something that we'll discuss later. Let's start by discussing how to plot the 1 plus s divided by omega naught term, which becomes equal to 1 plus I times omega divided by omega naught, if we again assume that our s variable is stable and that it only contains an imaginary oscillatory component. For very small values of omega, this function is approximately equal to 1, which means that its gain in decibels equals 20 decibels times the log of 1, which is 0 decibels. Because our function is again roughly equal to 1, this means that the phase of our function is equal to the arctan of its imaginary components, which are approximately equal to 0, divided by its real component, which equals 1. Thus, the phase of this function for smaller values of omega is roughly equal to 0 degrees. For very large values of omega, this 1 plus term becomes insignificant compared to the magnitude of omega divided by omega naught, which means that our function is approximately equal to I times omega divided by omega naught. When we take the log of this term, we see that our gain is approximately equal to that same 20 decibels per decade linear function that we saw when our s-domain function was equal to s in the previous lecture. Since our real component is approximately equal to 0, our phase is equal to the arctan of a large value, which is roughly equal to 90 degrees. When omega is equal to omega naught, our gain is equal to the square root of 2, which is just above 0 decibels. The phase here becomes equal to 45 degrees, which is right between the phases for low values of omega and high values of omega. So how can we finish the gain and phase plots for this example? We know that the gain is 0 decibels for low values of omega, and that it's roughly linear with a slope of 20 decibels per decade for high values of omega. So how do we make this plot? Simple, we just combine these two plots. As you see here, our gain is a steady 0 decibels for low values of omega, and it assumes a linear shape when omega equals omega naught. This is why this omega naught is known as the breakaway point, because it breaks away from being a constant. In reality, this transition is smooth and slopey, but we can approximate it as an instant transition to a linear function. Next, we know that the phase is equal to 0 degrees for low values of omega, equal to 90 degrees for high values of omega, and equal to 45 degrees right in the middle. So how do we transition between these two extremes? Well, we can approximate this transition as a linear function between when omega equals 0.1 times omega naught and 10 times omega naught. As with the gain plot, this transition is actually a fairly smooth and gradual transition, but here we can approximate it with just a linear transition. Similarly, the Bode plot for a g of s that equals 1 divided by 1 plus s divided by omega naught looks like this. Because our polynomial is now in the denominator, the gain plot has been multiplied by a negative sign, and the phase has also been inverted so that it ranges from 0 degrees to negative 90 degrees. In practice, we can use this kind of breakaway behavior to our advantage when we design control systems. For example, let's say that we're trying to design a low-pass filter, which filters out high-frequency signals by reducing their gain, and allows lower frequency signals to pass through. In practice, this kind of filter might be used for detecting low-frequency seismic waves or radio waves. Similarly, we might also want to design a high-pass filter, which attenuates low-frequency signals but not higher-frequency signals. In both cases, we can define the control element cleverly so that it delivers exactly the kind of signals that we want to see. Next, we'll consider a control element that contains a quadratic function of s in its denominator. Now, one might think that this function is simply equal to multiplying two 1 over s plus a functions together, but in this case, it's actually the product of two 1 over s plus a functions with a pair of complex conjugate roots. Again, these roots must be complex conjugates because of the plus-minus sign in the quadratic formula. The dampening ratio, or the squiggle variable, is defined as the square root of b squared divided by 4ac. And we'll see soon that the dampening ratio impacts the shape of the gain Bode plot. Now I said that we assume that these complex roots always come in pairs, as complex conjugates do. But it's worth asking if a system can ever have only a single complex root. This is technically possible, but in practice it doesn't really happen. The physical constants that describe a system's behavior are generally all real, and all imaginary roots will tend to come in pairs unless the equation in question contains imaginary components. So what do the Bode plots look like for a function with a pair of complex conjugate roots? Well, since our complex function is essentially equal to the product of two 1 over s plus a polynomials, it behaves very similarly to the product of two 1 over s plus a functions. At low values of omega, the gain is roughly 0 decibels and the phase is 0 degrees. And at high values of omega, the gain has a slope of negative 40 decibels per decade, and the phase is equal to negative 180 degrees. At omega equals omega naught, the phase is equal to 90 degrees, but something different happens with the gain. Instead of having a smooth transition from the low values of omega to high values of omega, we see this strange peak near omega equals omega naught. The height of this peak is equal to 1 divided by 2 times squiggle, which means that smaller values of squiggle will see larger peaks. This peak is nearly invisible when squiggle is greater than 0.5, and it disappears completely when squiggle is greater than 1.0. In fact, the complex roots also disappear when squiggle is greater than 1.0, becoming solely real roots. As expected, the phase plot starts at 0 degrees for low values of omega, and transitions to negative 180 degrees for larger values of omega. As with before, this transition is roughly linear, but here it starts at roughly omega naught times 5 to the power of negative squiggle and ends at approximately omega naught times 5 to the positive value of squiggle. Before, this transition happened at 0.1 times omega and 10 times omega, but here with this complex conjugate function, it begins and ends at different values of omega. Now let's finish our lecture today by repeating our exercise from the previous lecture and inferring the transfer function for some experimentally measured Bode plot. Here we're given a plot that starts at a constant gain for low values of omega, assumes a slope of negative 20 decibels per decade at some omega 1, levels off again at some omega 2, resumes a slope of negative 20 decibels per decade at omega 3, and then finally assumes a slope of negative 60 decibels per decade with a weird hump at omega 4. So what transfer function would produce this Bode plot? Well, we know that a flat gain means that our function is roughly constant at low values of omega, and we can use this initial value of the gain to solve for the constant, as shown here. At omega 1, we see that our function turns downwards with a slope of negative 20 decibels per decade, which means that our transfer function must contain a 1 plus I times omega divided by omega 1 term in its denominator. The gain plot levels out once again at omega 2, which can only happen if we have a 1 plus I times omega divided by omega 2 term in the numerator. Essentially, this positive term cancels out with the negative slope term from omega 1. The downward slope once again resumes at omega 3, which means that we must have a 1 plus I times omega divided by omega 3 term in the denominator. At omega 4, the slope turns from negative 20 decibels per decade to negative 60 decibels per decade, which either means that we have a 1 plus I times omega divided by omega 4 squared term in the denominator, or a pair of complex conjugate roots. However, the weird hump at omega 4 indicates that we must have a pair of complex conjugate roots, where the height of this hump can give us this value of squiggle in the equation here. So by looking at this one Bode plot and tracing the different values of omega naught, we have revealed the transfer function for a system that is some product of 4 different polynomials, I guess technically 5 if we include the gain. We get all of this just by looking at one Bode plot. This shows us just how useful Bode plots can be by using experimental measurements to infer the transfer function for some unknown system. This concludes our discussion of Bode plots. We've discussed how to generate some reasonably complicated Bode plots by hand, which we will do on some upcoming homework assignments, and later on we will use computational methods to generate Bode plots for some even more complicated systems. In the next lecture, we'll return to our discussion of stability criteria and see what Bode plots can tell us about a control system's stability.